Hey guys, welcome to Bio 112 Online, your home for biology education. Today's topic, electrical signaling in the heart. So as we're talking about the heart, we need to talk about the cardiac cycle. And the cardiac cycle, as we said, was going to be the rhythmic cycle of heart contractions and relaxations. We had described in the last video that this starts out through atrial and ventricular diastole, or relaxation of both the top and bottom pairs of chambers within the heart. This allows blood to fill the heart from the veins. The next stage will be atrial systole. Atrial systole will be the contraction of the atria pumping blood into the ventricles. This causes those ventricles to swell just in time for ventricular systole. Ventricular systole, that will be a contraction of the thick muscles in the walls of the ventricles, pumping blood into the artery. We also talked about the contraction of heart muscle cells in terms of what's going on at the cellular level. That contraction of those muscles is being directed by a wave of sodium ions moving from cell to cell to cell as a continuous action potential. As you have the depolarization of the membrane from that action potential, you then have the influx of calcium ions, which initiates the contraction of that cell. And in fact, all of the cells in the line at nearly the same time. In order to understand the sequence of mechanical events, what we also have to understand now is how that depolarization moves through the heart and what we would refer to as electrical signaling of the heart. This is going to start at the sinoatrial node, or the pacemaker. This is a group of autorhythmic cells in the wall of the right atrium, and it sets the timing of the cardiac muscle contractions, and it generates the electrical impulses. How does it generate an electrical impulse, you might ask? Well, it ends up being a little bit less nuanced as you might think. It's just simply a group of cells that are really, really lousy at maintaining resting potential. They will have a resting potential, however, that resting potential will tend to drift slowly back towards zero until it crosses the threshold. And once it crosses the threshold, you have an action potential. That action potential will then spread, starting at the SA node, then moving across into the atria. As that electrical impulse spreads from the SA node across the right and left atria, there's a wave of depolarization that induces the calcium influx into the cytosol. Actin and myosin are then able to contract within the atrial cells, resulting in atrial systole. Once that atrial contraction is complete, you then move into the next phase, where you have the activation of the atrioventricular node. The atrioventricular node is going to be a group of cells that, instead of being lousy at maintaining a resting potential, they're just simply lousy at passing along that action potential. As a result, this will delay the impulse of the electrical signal for about 1/10 of a second. This is going to be enough time to allow all those muscle cells within the atria to complete their contraction before sending the signal down to the ventricles. So once the AV node is activated, you then have the signal being passed down to the bundle branches. These are going to be a set of specialized muscle fibers that are kind of lousy themselves at doing the whole contraction thing, but they're really darn good at quickly passing an electrical signal as a wave. As they move that action potential down, conducted through the bundle branches, they move and then spread out through the Purkinje fibers. Those Purkinje fibers will then move that signal from the apex or bottom of the heart out into the walls of the ventricles. That wave of depolarization allows for the flood of calcium into the cells. The actin and myosin again interact, now in the ventricular cells, causing them to contract. This results in ventricular systole. What we want to do now is consider the cardiac cycle, that rhythmic cycle of heart contractions and relaxations, in both the terms of the mechanical and electrical signals simultaneously. We'll start off with atrial and ventricular diastole. Blood is flowing into the ventricles and atria via the veins. We then have the activation of the SA node. That activation of the SA node will spread a depolarization across the atria, resulting in atrial systole. This pumps blood from the atria into the ventricles. We then have that signal pass to the AV node, down the bundle branches, through the Purkinje fibers, causing a depolarization and contraction of those ventricular cells. As those ventricular cells contract, we then move into ventricular systole. As we move into the ventricular systole, we then have the AV valves slam shut. The semilunar valves are opened and blood flows from the ventricles into the arteries. In order to view this, often doctors will use what's referred to as an electrocardiogram. An electrocardiogram, either described as an ECG or an EKG, depending on where you are, is going to be the measurement of the electrical signals in the heart using electrodes placed on the skin. We can visualize these series of events by taking a look at a series of electrical waves being detected on the surface of the body. The first of these electrical events is referred to as the P wave. That P wave corresponds to the depolarization of the atrial cells and corresponds inherently to the atrial contractions or atrial systole. The next wave is going to be referred to as the QRS wave. The QRS wave is going to be due to the depolarization of the ventricular cells and will be also due to the repolarization of the atrial cells. This will correspond then to ventricular systole, as you have the signal move down the bundle branches through the Purkinje fibers, causing the ventricular cells to contract and the ventricles to go into systole, pumping blood into the body. The next wave that we want to look at then is referred to as the T wave. The T wave will represent the repolarization of the ventricular cells and will correspond to atrial and ventricular diastole. The electrical and mechanical events of the heart work together to ensure a constant flow of blood throughout the body, a circuit that will take the blood from the heart to the lungs, back to the heart, and then to the rest of the body, providing the resources cells in the body need. But that is the topic of the next video. So until then, stay safe, stay healthy, and I'll see you later. It's alive. Alive.